All right, I want to talk a little bit now about some more advanced architectures. And before I do, I want to talk about the difference between cosine and sine. So we've already covered the convolution of cosine and the fact that the Fourier transform of cosine has two delta functions, both pointing upwards on the positive and negative half of the omega scale. And just once again, just to remind you, these come from e to the j omega t plus e to the minus j omega t over 2 is equal to cosine of omega t. And you can see we've got our positive and we've got a negative right here. Okay? That's just one way to think about it. But now let's take a look at sine of omega. And you notice here something a little bit funny. And you're probably used to seeing sine with the two arrows being opposite, but I've put them at an angle here. And the reason I've done that is they actually have a magnitude j. And the reason I did that is I'm basically representing up and down as the real axis, if you will, and this as the imaginary axis. So this is just a way I like to show sine because it reminds us that we have a complex or an imaginary component here. And if you do the convolution of our original signal, you get it basically placed in this complex plane here. And so you can see we have this has a complex magnitude, this has a real magnitude. Just to be clear, they both are real signals because they have a negative and a positive frequencies that match. It's just that if we set cosine to be real, then sine is orthogonal to it, and that's where we get this j. And there's a little bit of trickery we can do with this, because if you look at these two signals, what would happen if we tried to put the two on top of one another? And so here all I've done is taken a signal from before and added the two together. And you can notice I've got my cosine signal here and I've got my sine signal there. And I've drawn it this way because graphically you sort of say, oh, well, I could actually transmit these two signals, and if they're orthogonal, because one's real and one's complex in value, and once again, all that means is one is phase shifted from the other by 90 degrees, I can actually transmit both of them at the same time and not lose any information. And in fact, that is exactly the case. And this is what we call quadrature modulation. And typically what we call the cosine is the in phase, and then we call the sine component the, actually, let me erase this here. We call this one the in phase and this one the quadrature because it has a 90 degree or pi over 2 phase shift. And you can see it right here. Now, if you're like me and you're looking at this cartoon, you're saying this is all well and good, but what does it really mean in the time domain? I actually wanted to show you what it does mean in the time domain. And what I've done here is I've drawn a cosine in red and a sine in blue. And let's imagine that I was looking at just the envelope, just the peak of the two signals of the cosine and the sine. When I want to go look at the cosine, that's the red one, I'd look at this point in time. And notice the sine is 0. So that means any signal I receive at this time is just from that cosine component. Just like if I go to this point in time and I look at a signal I'd receive, I would just be seeing the sine component. So you can see kind of in a easy fashion here that because these are phase shifted and one is 0 when the other is not, and vice versa, it's kind of clearly easy to see that I could transmit a sine and a cosine and get different values of the amplitude from the received signals. I think that helps out give a little bit of a intuition. So the next thing I want to talk about is something called a single sideband. Now, before we removed the carrier, and the main purpose of that was just to reduce power. Why transmit the carrier if it doesn't contain any information? Another thing that we might want to do is not transmit both sidebands. So what do I mean? Well, if you remember, our original signal looked like this, right? So this was our original signal. When we up convert it, we get this half and this half. And so here we knew that these two were just a mirror of one another, right? So this is just this is omega equals 0 right in the center, and so 1 was just a mirror here. But if you look at it now, we've got 4 copies of this, but we only need the 2 halves to recreate the signal. So one thing we might want to do is come in and maybe filter out these extra sidebands that we don't need. And so here's a magic filter, and basically we're going to transmit everything in this region and this region, and we're going to filter out everything in here. And so basically we're going to transmit this, and we're going to transmit this. And so here's what comes out of our filter. And if you remember our coherent receiver, we can just use a coherent receiver just to downconvert and recreate those. And so from here, it's probably really easy to see that we only need 2 bands to recreate the signal, and that this double sideband that we created from up conversion just creates an extra copy that we don't need. So this is a great idea. We can get rid of the carrier if there's no DC. We can get rid of the extra sidebands because we don't need all 4 here. What's the challenge? The challenge is this word here, magic. You really need to be able to filter out the sideband you don't want. And in reality, most of these filters are going to look like this. And so you're not going to have a perfect removal of the sideband. And so you have to deal with some of the non-idealities of that. But still a good idea. And it turns out there is another, a little bit more interesting way to try to get rid of these copies by playing a little bit of complex math. And so I want to talk to you about that. But before we do, I want to talk a little bit about cosine to sine, and specifically some different ways that we can represent a phase shift. And this will have to do with some insight into some architectures for single sideband. So if you remember, cosine of omega t could simply be written as e to the j omega t plus e to the minus j omega t over 2. Now what we can also do is we can also take cosine of omega t and add a phase shift. Okay, let's just draw that real quick. So here is cosine, right? And I'm going to change my pen color, and I'm going to just shift it to the right by 90 degrees, right? And you can see clearly that that's simply a sine of omega t. Okay, and that's something that we're pretty familiar with. But let's look at this representation and see what happens when we do that mathematically. So let's take e to the j omega minus omega t minus pi over 2 plus e to the minus j omega t minus pi over 2 over 2. All right, now let's just multiply that out. We get e to the j omega t e to the minus j pi over 2 plus e to the minus j omega t e to the j pi over 2. This is all over 2. Now you may be stuck here for a second saying, what the heck does e to the minus j pi over 2? Or maybe you're saying, I don't know. Okay, so let's just look at that from Euler's formula. E to the j phi is equal to cosine of phi plus j sine of phi. Okay? Now let's try it with pi over 2. E to the j pi over 2 is equal to cosine of, pi over 2 plus j sine pi over 2. Well, you know what this is equal to. Cosine of pi over 2, it's right there, is 0, and sine of pi over 2 is 1. So plus j. And likewise, we can find out that e to the minus j pi over 2 is equal to minus j. Okay, so let's go back and take a look and plug that in for our e to the j pi over 2. And I now have minus j e to the j omega t plus j e to the minus j omega t. All of that is over 2. And now what I'm going to do is I'm going to take these two j's and I'm going to bring them down below. And if you remember, if you put j on the bottom, that just gives you a negative. And so this gives me a nice e to the j omega t minus e to the minus j omega t over 2j. No, sorry, 2j. And you should recognize that immediately as just being sine omega t. Okay. Why did we go through that? Well, what I wanted to show you was doing a phase shift of pi over 2 ended up changing our exponentials by a minus j and a plus j. And so if you look at cosine, where we've got this, we've got this, we've multiplied this one by minus j, and we multiplied this one by j. Now, a convenient way of showing this is to actually draw this sort of a 3D form where I could say that this is minus j and that is plus j, and call this sine omega t. And the reason why I do this at this sort of 3D angle is this way I can think about this as being the real axis and this as being the imaginary axis. And once again, both sine and cosine are absolutely real. It's just they're orthogonal to one another. Sometimes when we're dealing with complex numbers, that complex number just allows us to deal with an orthogonal component. And so what we can see is this phase shift actually just takes this, rotates it down, takes this, and rotates it down. And using that now we can get some insight into what phase shifting a signal might do to its spectrum. Back, you can see what a minus pi over 2 is going to do is it's going to give us a complex and also swap the polarity. And so what it does is it rolls this half down there and it rolls this half down there, and I get that. And if you're having trouble following that, you can see it's exactly what sine does. So basically, if you can think about if here's cosine and I put in my 90-degree phase shift and it turns it into sine, you can sort of see this rotated down, and you can see that's exactly what happened here. Now, I then multiply it by sine. Okay, these two have zero connection with one another. All right, so we may be very clear about that. That this is what we have here. This is the signal that comes out here. This is the signal that goes in. This is all about this multiplication. The reason I do that is if I have this being equal to j and j times j is what? It's minus 1. And so we end up with minus 1. And now I have minus j times minus j gives me a plus. And so this ends up here. And likewise, if you follow through, I get this pattern here. And so now I've created a version of this spectrum that is just like this. You might be saying, okay, but why do I care? I mean, this is what we used to have, right? And this is what we have now.